Thank you. Yep. My name is Ben Dymond. I usually start introducing myself by saying that I'm from Minnesota, and in Minnesota I'm at the most northern point of Minnesota, almost, which in the United States says I'm almost the most northern school, but this is actually north of where I am, so that doesn't work here. But I'm in Minnesota Duluth. We're on Lake Superior. It's a very beautiful place, and I'm going to talk to you today about shear distribution after damage to prestressed girders. So a little bit about the outline and talk. I'll do a brief introduction and some motivation and background, tell you kind of the goals for the research, and then get into the experimental program and results, and finally some conclusions. So what am I talking about? Shear distribution means not flexure, but shear, obviously, and then the goal is to look at a bridge and see how the shear loads distribute from traffic or trucks to each individual beam. So I'm trying to estimate the force on individual girder from the traffic. So for example, I've got a truck driving across here, but really what I'm interested in how the shear force from the truck is distributing amongst 5 or 6 or 7 beams. But this is a complex problem, as you can imagine, because a bridge isn't just beams and a deck and a truck. There's numerous parts to the system. So with that, it can be affected by a lot of things. And this talk really will focus on a few and the overall behavior, but it can be affected by primary elements, such as obviously the beams, the deck and the span length and the deck thickness, but also secondary elements, so things like intermediate or end diaphragms, and we'll talk a little bit about that today, or traffic barriers. In the United States, at least, this is often estimated using what's called a distribution factor, or in my short terms here, a DF, where it's really just an equation that's derived from elastic analyses. So no failure loads, no cracking, just elastic behavior, come up with an equation for distributing the shear force. So with that in mind, I'll go a little bit into the motivation here. This side of the project really was looking at load rating. So if a structure, or evaluation I suppose, if a structure exists, the goal here is to find out the safe live load carrying capacity of that bridge. So how much weight, how much truck traffic can go across. Where I'm from, some prestressed concrete girders rate low for shear, meaning if you run the numbers in an equation, the final value says, your bridge isn't performing as it's supposed to. But if you go in and look at these prestressed girder bridges, there's not a lot of cracking. There's really none observed during inspection. And for the most part, the bridges aren't falling down. That would be in the national news. So something is disconnected here. And that's one of the main questions is there some additional shear capacity in the system, so for shear specifically in the girders, or is there some conservatism or disconnect in the way that we're distributing the load from the traffic to the individual beams? So kind of a two-part question. So load rating is thinking about a few things, and there's a very general equation here and with a few important things in that yellow shape. The first one is that I previously mentioned these distribution factors, which are equation-based in the United States, come from elastic behavior, elastic modeling. So that's how you get your truck load into an applied live load shear. So if you wanted to rate for shear, the applied load is the live load. That V sub LL is for live load comes from an equation that's elastic. And that's on the bottom of my rating factor equation. And it's also mixing then in the capacity of an individual beam, which is designed for ultimate load, right? So there's ultimate and elastic or service, which is the phi VN here. So in the equation for rating, I've got the capacity of my member minus some dead load divided by the live load. So we're mixing and mingling elastic and inelastic behavior. So that's the second question. Is there some conservatism related to using these elastic distribution factors at ultimate behavior or trying to rate the structures in this manner? So the goals for the talk today were twofold. The first one was to experimentally determine if an interior bridge girder distributed or shed shear force to adjacent ones as that girder cracked and went towards ultimate failure or destruction. And the second one was then to quantify how a partial depth end diaphragm, so I'm thinking about shear near the end of the span, an end diaphragm affected that distribution. Did it help or hurt or not really have an effect? So those were the two primary goals. I will talk a little bit about the web shear cracking and patterns. We talked a little bit about cracking and wasn't observed, and I'll talk about that coming up just a bit. So the way this was done was in a laboratory. There was a full-scale end or approach span structure built with no skew, so it's a straight bridge. End or approach span means if you're thinking about a highway structure, usually there's a longer span that crosses the river or the roads beneath, but there's often often two approach spans that lead up to the longer span. So this is the shorter spans that consist of 4 beams, 3 feet deep, with an end diaphragm on one side of the structure, and the one that's not pictured, the other end did not have a diaphragm, so we had a direct comparison of each. The beams were spaced at 9 feet on center, and the span length was about 32 feet. And some of this was limited by the fact that this is full scale in a lab, so we can't do humongous, but pretty good scale. The primary instrumentation plan for the structure was putting on vibrating wire strain gauges, which record strain to a very small and fine detail, but we put them in a rosette pattern because we're shooting for shear behavior here, with the goal of capturing vertical shear strain due to the applied shear. These rosettes were applied in a grid, both transversely, which means on every beam, so if there's 5 beams on each beam, but also longitudinally along the length of the structure, associated with the critical section for shear, so that's D sub V in AASHTO code. So every couple feet or so. Load was applied with all of the actuators we owned to try and fail the structure, which was great. But that's what it looked like, from a picture view. But really, what it's doing over there in the top right is applying all of the load over top of an interior girder, recognizing that if we apply the load elsewhere, we're just pushing down on a 9-inch thick deck, and it's not really going to do us much good. The load was applied about a shear span to depth ratio. If you're thinking about height of 2.5, or if you're thinking about the effective shear depth of 3, so trying to keep the load away from the support such that the load doesn't go straight to the support. It has to travel through the stirrups and the girders to get to the support. We were focused on an interior beam I mentioned before, and one of the secondary goals here was to investigate both ends of the structure, so what happens with an end diaphragm and without. And there's 4 beams in the structure. We loaded over an interior girder on one end, switched and loaded over the opposite interior girder on the other end, so kind of kitty corner or perpendicular quadrants of the structure. So some results. The failure mode was interesting. It's been reported in the literature, so there is a paper behind this in the SP that I mentioned, and there is some background and literature review that I didn't want to present today. But this failure mode isn't uncommon. What happened was when we hit the right load, there was simultaneous deck punching above the interior girder, but also a web shear failure in the beam. So you can see there's 2 pictures. The left shows the top of deck punching, so the actuator kind of applied load area punched through the deck on top of the girder, and then below, with the 2 arrows there, the A and B is kind of the area that punched on the bottom of the deck. But simultaneously, there was a web shear cracking and failure in the interior girder that was loaded. And it's impossible, or from my point of view, was at least to determine which happened first or which led to the other. But the literature saw similar failures in this mode. What that means, though, is that after the deck cracked and punched, it couldn't continue to distribute load to the adjacent beams, right? It's totally going to focus on the one that broke. And what was really interesting is that there wasn't any web shear cracking in the adjacent girders, only in the primary loaded ones. So the 2 next to the beam that we were loading were uncracked, theoretically still elastic. So if the deck hadn't punched, perhaps it could have still pushed load to the adjacent beams. And obviously, we're applying much more load than a wheel patch from a truck. So it's a little bit different from bridge loading, but looking at distribution. So here's a big picture that I'm going to take some time to explain, and there's a follow-up one, which is looking a little bit at how the shear redistributed after cracking and just prior to failure. So on the x-axis, I've got the shear force in each beam that was calculated with the instrumentation. So if we're looking at the one I loaded, what's the amount of shear based on shear strain, converting that to a force. On the y-axis, I've got the total applied load. So as we keep going up and up and up, how much applied load do we have? And then there's 4 lines that kind of have nice shapes of triangles, diamonds, squares, and circles, which each correspond to a beam in the bridge. So that's the picture below where we've got girders number 1 through 4. And this one specifically talks about having an end diaphragm in the cross-section. So that's this slide. The next slide will have no end diaphragm. What's really interesting from this is that you can kind of assume right away we load the beam or the bridge and we go up until we observe cracking and everything's linear and elastic and behaving fine. Each girder is carrying an appropriate amount of load. After we've observed cracking, the slopes of these lines start to change, which means that some of the girders are carrying more load, some of them are shedding load. And what's the most interesting is the line to the far right, which is the primary loaded girder, which remains very linear until cracking, and then it starts trending with a different slope upward. And that means that along the x-axis, the amount of shear it's carrying is decreasing. It's not staying a low slope. And the 2 lines that are triangles and squares here, one over, have a slope before cracking, and then after cracking, the slope changes and goes a little bit more shallow, which means that along the x-axis it's carrying more load. So we're shedding load from the interior girder to the exterior and adjacent interior beams. The difference in load that was shed was an average of about 90 kilonewtons to each beam adjacent to the primary interior girder. So then the calculated shear force at failure for this particular cross-section with a diaphragm was about 916 kilonewtons, and we'll compare that to the next slide. So the next slide is exactly the same picture. It's almost, did I really push a button or not, but I did. The picture below just doesn't show a diaphragm. So this is the same exact data, opposite end of the structure, different beam that's primarily loaded with no diaphragm. So the behavior is exactly the same. The primary loaded girder is linear, it cracks, it changes slope, starts carrying less shear force. And one thing I didn't mention is that we did extrapolate that linear line so you can kind of see visually a difference in if it had remained linear versus now it's starting to shed load to the adjacent beams. And again, the average load difference in the two adjacent girders is roughly 90 to 100 kilonewtons. So the interior girder is shedding load to the adjacent beams. So how did the diaphragm affect this? I talked a little bit about the applied load. Sorry, let me go back one here. The calculated shear force at the very top there was 939 kilonewtons, pretty close to the one before, which is about 916. Very top point up there, and I'll cover that one more time here. But the diaphragm seemed to not have a large effect in that the total applied load at failure on either end was about the same. And that's shown in the parentheses down there in blue. No end diaphragm failed at about 2,000 kilonewtons. With an end diaphragm failed at about 1975 kilonewtons, within 10% of each other. What was most interesting to me wasn't the numbers in these comparisons, but the actual pictures. So what happened, the end diaphragm side of the structure is on the right, and no end diaphragm is on the left. And the red arrows indicate internal stirrups in the prestressed girder spaced at about 2 feet. So we're trying to fail it in shear. We don't have a ton of demand we can apply. But the cracking pattern was quite different with a diaphragm and without. With a diaphragm on the right over there, the web shear cracking pattern was much higher in the cross-section. So you expect it to be in the web going diagonally. This one penetrated the top flange quite extensively. So there's 3 lines. You can see cracks, right around that middle stirrup red arrow with an end diaphragm. So that's pushing the load towards the center line of the support. So center line of the bearing. In shear, we often associate the bearing as the face of the support. And so on the left, without an end diaphragm, the load traveled much lower in the cross-section through the web of the girder towards the face of the support. So that's the same 3 stirrups. You can see the cracking patterns below all the arrows on the left versus kind of going up towards and into the top flange on the right. So the conclusions that I found here are the differences in the applied load were only 10% or less, considering with or without a partial depth end diaphragm. There was definitely shear redistribution after cracking as that damaged girder continued to be damaged and head towards failure. There was an inherent factor of safety that's really tough to quantify because we're not applying a truckload like design codes do, but there was definitely an inherent factor of safety from elastic behavior to inelastic behavior, which means that these linear elastic shear distribution equations were conservative, right? You have a nice factor of safety, go home warm fuzzy at night and sleep well when you're thinking about the ultimate limit state. So with that, I'm happy to answer questions. And what we didn't say in the beginning is when you ask questions, please come up to the microphone. We are recording it. So.
Thank you. Very good presentation. I just curious, when you load the interior girder, do you on purpose load perfect center along the girder, interior girder line, or you trying to offset a little bit so that diaphragm can detect potential torsional effect?
Yeah, great question. We purposefully loaded over top of the girder, and this study was much bigger than this. And what we did see with diaphragms and even without, when we're loading between them, there was a lot of elastic loading that validated a finite element next to this, and this is one part of it. There was definitely torsion in pre-stressed girders, and I'm happy to talk about that later. There's other publications, and we've seen, even though they're very stiff beams, we've seen them twist, and with this fine detail instrumentation, we were able to record that. But we purposely, in this one, loaded over top of the girder.
The loading that you placed over top of the girder, you had 3 actuators. Mm-hmm. Were they lined up on the center line of the girder, or were there was a diagram here. Well, just go back one slide.
Oh, the applied load, or
yeah, where the applied load right there. You see, it looks like they were applied on either side of it, and so you have stiffness of the loading frame itself. Was that did that influence the punching shear? Was that what did the loading rig actually flex and cause the punching shear?
The loading, so the way it worked is that below, so I removed the frame you're talking about, or the steel beam below the picture here. The steel beam came down to a neoprene patch, which was pretty much that size. You can see the arrows on the left picture, 91 centimeters and 30 centimeters. And we just physically couldn't apply the load in a smaller area. So it definitely influenced the punching in that that's the surface it punched. Had it been over the deck, as the first question suggested, we probably would have punched straight through the deck and not applied the load on the girder. So we kind of did the best we can. An ideal scenario would have been to apply this magnitude load with several actuators spaced like an axle or axles, but that's even harder.
So to follow up on that,
Yep.
how do these loads compare to the actual wheel loads that would be applied to a bridge deck?
Sure, great question. They're significantly higher. The wheel loads, an axle load in the US code is about 32 kips divided by 215 kips. This point load that we went up to was about 450 kips in one spot, so vastly different. So there's a huge margin of safety in that regard, which is also talked about in the paper behind this. But yeah, this is really trying to investigate what happens after elastic behavior.
I'm just curious, did you reinforce the deck so that the deck would properly distribute as in a real case?
Yep. I didn't mention much detail about the deck design, but it was 9 inches thick and had the normal reinforcement the state of Minnesota puts in a 9-inch thick deck, transversely and longitudinally. So it itself should have been able to handle, to a certain point, what we did.
Similar question on your girders. Sure look like pretty widely spaced stirrups for the end of a pre-stressed girder. Was that intentional, or is that still satisfy whatever AASHTO shear requirements?
Yep, great question. It was intentional, yes. Did it satisfy AASHTO? No. It satisfied the maximum load that we could apply. So we had to, it was kind of a capacity-based design in that I knew I had 440 kips and I couldn't go above that. What was interesting that I didn't mention is we did some other tests on beams similar that went down to like an 8-inch spacing or something much more normal for the end of a girder. And when that tight of a stirrup spacing was available, the first web shear crack that appears, if we unload the structure, kind of disappears. So it may not be visible if you have an overload and not. But with this really wide spacing, we had a unique chance to see, hey, if we crack the girder and take the load off, can we still see it? In which case, yes, without more stirrups. Okay.
Thank you very much.
Dan, for this.